Okay. Well, they also often have magnesium, iron, or potassium in between the layers, or sometimes on the surface, or sometimes they substitute the lattice itself. So normally they go in place of aluminum. So silicon and aluminum in different ratios form the basis of the structure. So we have different clays is because we have silicon and aluminum, but they are in different ratios, giving rise to different kind of clays. They form in soil and sediments and by diagenetic or hydrothermal alteration of rocks. So rocks also has this material, this aluminosilicates. And then if these rocks, for example, they are inside the ground, okay, which means that they are going to feel pressure and they have water. You remember we discussed hydrothermal method is something like pressure cooker. So if you consider a rocks which is below the ground and suppose they are exposed to water, groundwater. So this situation is something like pressure cooker or hydrothermal condition. So in those conditions, this clays form. Structurally, the clay materials are composed of planes of cations arranged in sheets. You see, the planes of cations arranged in sheets like graphene sheets, which may be tetrahedrally or octahedrally coordinated with oxygen. So these cations, aluminum and silicon, aluminum usually prefers octahedral holes and silicon usually prefers tetrahedral holes. So these sheets that we are talking about are actually sheets of this polyhedra, not the metal atoms alone. And these polyhedra, they share their corners or their edges, some aspects, which means they share the oxygen atoms, which in turn arrange into layers often described as 2:1. If they involve units composed of two tetrahedral and one octahedral sheet, we'll get to the picture, we'll see it. But normally, roughly, the silicon is to oxygen ratio is something like 2:1 or 1:1. If it is 1:1, if they involve units of alternating tetrahedral and octahedral sheets. Additionally, some 2:1 clay minerals have intercalated sites between the successive 2:1 units, which may be occupied by interlayer cations, which are often hydrated. So, as we said, these are layered materials. Sometimes, because we need to do charge balance, aluminum and silicon has different charges. If charges are not balanced, what happens? Some other ions go inside it because they form in presence of water, and water often has other cations. So these cations also get inside these layers. So as a whole, the entire thing is called clay. So in summary, we have the tetrahedral structures of silicon and we have these alumina octahedras. Okay, this you can see this tetrahedra connect to each other by sharing corners and they form a sheet. Similarly, the octahedras, they share faces. They do not share corners, they share faces and forms a sheet. Now, if you take a tetrahedral sheet and if you take an octahedral sheet and put one top of the other, you get a single layer of clay. Now, if you put many layers like this, you end up getting what is called the clay crystal. Kaolinite clay are called 1:1 phyllosilicates. Okay. This is kaolinite is what is available in nature. Okay. So you can look at this picture. You can see is this schematic where you can see the difference between 1:1 and 2:1 clays. And you can see here on the left hand side, it looks like a house, a multi-storied house. So the roof is actually nothing but alumina layer, because you can see from the top that they are tilted. And the middle one is basically silicate layer. Similarly, 2:1, you see the silicate layer is in between, covered by, sorry, I told wrongly. The one which looks like roof is basically silicate layer, and the one which looks like I don't know what is it called. The in-between layers, if you see it in the right hand side, if you see the in-between layers are the alumina octahedras. Okay, and you can see on the right hand side picture that sometimes you have some additional cations in between the layers. So basically the two different kinds of clays. So now what is important is to consider that the tetrahedral side, that the tetrahedral coordination of silicon is very important in developing these clays. Okay, and you have, I think you have studied in CSM 303 the silicon chemistry. So it forms an tetrahedra with 4 oxygen atoms surrounding it, and if they are independent, you can consider it as SiO4 4 minus, because silicon has 4 plus and oxygen has 8 minus. So overall SiO4 4 minus. Now using this, the smallest motif, we must now move forward and we have to make the complex motifs. Now one case you can see here, two tetrahedras are connected and they are corner sharing. In this case, this unit is Si2O7 6 minus. Because oxygen is being shared, the charge has reduced. Similarly, if you have Si6O18 12 minus, and it forms the third structure, which is something like a hexagon, and is one of the basic and fundamental unit building blocks. And sometimes you can also have corner sharing, two corner sharing change. Okay, and all these building blocks can be found in clay structures. So this is again, nobody is expected to remember these names. Okay, just to have a feel that you see there are different types of 1:1 or 2:1 clay structures. 1:1 the number is less. 2:1 there are many. For example, if you look at the third from the top, is talc powder, which is whose composition is 2:1. Mica, many of us know mica. I think you have used it in some experiment, in some summer project or something. So mica is again is basically 2:1. But there are deficiencies. Okay, so X represent deficiencies. We'll see what X is. This is not perfectly 2:1, but the structure resembles 2:1, which is the aluminum layer is sandwiched between two silica layers. Okay, this is how these minerals are classified. So this is a structure of phyllosilicates. Have I shown here phyllosilicate? No, okay. So this is a phyllosilicate structure which has, as I said before, aluminum and silicon, but some magnesium is replacing the aluminum side. So all these replacements happens in nature because of the hydrothermal conditions. We really do not have a control. For example, if you go to a region in Earth where the content of magnesium is more, you are going to get this kind of place. So here you can clearly see uh, the aluminum. If you look at the left, you can see the aluminum octahedral layer and the silicon tetrahedral layer. And these two layers share one oxygen atom. So within the layer, they share oxygen atoms. Aluminum octahedral shares faces, which means they share 3 oxygen atoms, right? Then only they can share faces. And between the oxygen and silicon layer, they share 1 oxygen atom. Now, there are some oxygen atoms, but charge is still not balanced. Okay, and therefore, you have the hydroxyl layers. You have this hydrogens attached to this OH, the oxygens. So overall, it is a hydroxyl layer because this is ONH. Okay. So these hydroxyl layers you can found in those oxygen atoms which is not part of the tetrahedra. So on the right hand side, you can see this structure more clearly. Okay. So kaolinite, for example, or which is called China clay, can be represented as, because it has some OH groups. Okay. This is, instead of O, you can consider them as OH. Okay, because it has some additional charge, negative charges, so it absorbs some protons. So the China clay, the formula is actually Al2OH4 Si2O5. Okay, so aluminum octahedral and silicon tetrahedral side. Now you can, this structure is more simplified. Okay, so you can see on the top the tetrahedrous made of oxygens, and the black dots are basically silicon. Similarly, you can see this aluminum which is in an octahedral hole, because you can see 1, 2, 3, 4, 5, 6 oxygen atoms. So this is an octahedral hole, and this in this way this layer stack. And I have also indicated where OH ions bind. For example, in between layers, they are not sharing anything, right? In between layers, because the gap between two layers is pretty much high, so they cannot share the oxygen atoms. In this case, the OH ion comes and sits, the H ion comes and sits on these oxygen atoms. Okay. And I have indicated the aluminum side. In place of aluminum, sometimes we have magnesium, for example. Okay, and you can imagine when you put magnesium in place of aluminum, the charges are different. So this OH, the number of OH groups are going to change accordingly. Now, in this slide, I'll roughly show you the difference between a 1:1 and 2:1 structure. So the top one, the left hand top one is this kaolinite. It has so you can see it. So it has silicon tetrahedra. You have seen it have aluminum octahedra, and you have these oxygen ions, oxygen atoms, which are exposed. And because see the gap is, this is almost crystallographic dimensions. Okay, and you can see the gap between the two layers is pretty high. So that's why they cannot share oxygen atoms. So it has oxygens with negative ions. Similarly, on top of side, we also have oxygen atoms with negative charges. So, depending on the number of charges, okay, some of these oxygens will take protons. Okay, all oxygens will not be taking proton because we do not need that much in the structure. So only some of them are going to take protons. So therefore, there is a hydrogen bonding between these two layers, because on one side you have OH, in the other side you have O, and this hydrogen bond makes these layers strongly bound to each other. And that's why, for example, in ceramics, the bone china, we have this kind of utensils in our homes, which is made from china clay or bone china. These are common names, which contains kaolinite, and they are strong because they have hydrogen bond. Now, if you come to the right hand side, you see this is 2:1. Okay, in this case, we have, in this particular structure, all aluminum is gone and all aluminum is replaced by magnesium. This should not bother you, because if you replace aluminum by magnesium, what changes is only the charge and the OH groups. If it would have been magnesium, aluminum, the structure would still have been same. So here you can see you have the octahedral sheets in between two tetrahedral silicon sheets. Now, because this structure is like this, there are no OH groups. Okay, this structure is in this case, the charge is already balanced. So the charge is already balanced, and there are no OH groups. Okay, and because there are no OH groups, not in the layers. Okay, and because there are no OH groups, or sometimes depending on the stoichiometry, there are very few OH groups, the hydrogen bonding is very, very weak. And because hydrogen bonding is weak, they can exfoliate, they can separate from each other. They are slippery. The powders are slippery. This is one of the reasons. So our original intention was to discuss nanoporous materials. I just want to define what is nanoporous material. The clays, to some extent, we can consider them as nanoporous materials, because the layer can be considered as pore, where the dimension, the thickness of this pore or the width of the pore is less than a nanometer. So it will be something like 0.5 nanometer or something like this. So nanoporous materials in general consist of regular organic or inorganic framework supporting a regular or porous structure. So it can be inorganic as well as organic material, and support it should have pores which are regular, which are regularly arranged within the structure. So pores are defined by definition roughly in the nanometer range. That is, you can say from 100 nanometer, from 0.2 nanometer to 100 nanometer, in this range. Okay, 0.2 nanometer to 100 nanometer, in this range pores should be there. So these pores, because the difference is very high, 2 orders of magnitude, more than 2 orders of magnitude, they are further subdivided into 3 different parts. Okay, they are called microporous materials, such as zeolites. Okay, mesoporous materials, and macroporous materials. So this name, you'd see that the names are quite misleading. Microporous is supposed to be, the sizes should be something like micrometer size, but actually the smallest sizes 0.2 to 2 nanometer, they are called microporous materials. Then 2 to 50 nanometer, they are called mesoporous materials. And anything 2 to 50 and anything more than 50 nanometer pores, they are called macroporous materials. So let us start by discussing zeolites. So you can look at the structure on the right and you can immediately see this is a crystal structure of some zeolite, and you can see these are the pores. You can see the pores there, and these pores are actually channels. So this will go throughout the material, and because of these pores, which are big enough to contain many ions as well as organic molecules, small organic molecules. So they give rise to diverse kind of applications. So this is another example of aluminosilicate structure, framework structure, where again, just like clays, we have silicon and aluminum. So zeolites are groups of crystalline aluminosilicates with group 1 or group 2 elements as counterions. Okay, so here again, we have to have counterions because of the way this silicon and aluminum polyhedra are arranged. You should remember that there is a big difference between clays and zeolites. In zeolites, silicon and aluminum both are in tetrahedral sites, whereas in clays, only silicon is in tetrahedral site, whereas aluminum is in octahedral site. So they consist of frameworks of SiO4 and AlO4 tetrahedra linked to each other at the corners by sharing their oxygen. So the presence of trivalent aluminum ion gives rise to surplus or negative charges, hence the need for counterions. So zeolites by default contains counterions, which comes from the group 1 or the group 2 elements. So zeolites have many different structures. All have open pores or cavities in regular arrangement, having similar size as small as a molecule. So there are about 40 naturally occurring zeolites forming in both volcanic and sedimentary rocks. And in fact, initially it was discovered naturally, and then learning from nature. So researchers have started developing artificial zeolites. And DuPont, for example, DuPont is a pioneer, DuPont company, and they have developed a large number of zeolites, and now you have zeolites. Just hold on for a minute. Yes, please.
Some patent will.
Oh, okay.
And he's waiting. He's standing outside. You have to sign it.
Oh, you tell him that I have a class going on, so I will take it after class. Okay. You can give me this one.
He's waiting. Okay.
You tell him that we will give him back. So, so this is a very interesting example, and I think you will realize by the end of this class that something which was seen in nature, how people have modified it, and it has been used. It has tremendous uses. So the natural zeolite looks like this. You can see on the top right hand side, and the artificial zeolite looks like what you see in the top left. Okay, they are like molecular ships. Okay, so they are used as catalyst okay, because of that particular pores, selective absorbance, okay, they absorb something selectively. हाँ क्या चीज अच्छा अच्छा मुझे 4 बजे तक मेरा क्लास है so selective absorbance, okay, ion exchange which is used for water treatment, okay, and as a catalyst support, if it itself is not a catalyst, it supports the catalyst, for example in car engines and stuff like this, okay. So this is the most important class of catalyst in industry. So it is also used for carrier of ions. Okay, you can carry ions from one side to the other. It contains acid sites of strong acidity, okay, for catalytic reactions. And we discussed this. The origin of this is that it says uncompensated charges. So it takes these protons, and these protons are highly acidic, and they are very useful in catalysis. So these protons can be replaced by sodium, for example. And on the right hand side, I show you a crystal structure. Okay. One of the basic zeolites. Okay. And we'll come to this structure later. So all zeolites contain water. So let us see how this silicon, this zeolite structure come about. Okay. So in the top row, I saw that this silicon tetrahedra, they are connected by sharing their corners and forming some kind of a hexagonal ring. Okay, it is not a perfect hexagon if you see the conformation, but roughly you can consider this as a hexagonal ring. You can understand that this is not perfect hexagon because the angle around silicon is a tetrahedral angle. Now you can decide to replace some of the silicons with aluminums. In this picture I show one silicon is replaced by one aluminum, or in the next one 3 aluminums. As a consequence, it develops these charges. So in the bottom, I showed schematically, this is like a hexagon. And you can see this molecular structure, this is a model molecular structure where you have silicon and aluminum surrounded by red oxygen atoms. And there are some either protons or some cations, counter cations are going to be there. So when tetrahedral silicon 4 is replaced in a silicate by an tetrahedral aluminum, the framework attains an extra negative charge. This will be compensated by a cation such as sodium plus. Such compounds are termed framework aluminosilicates. So we discussed before, please note that both aluminum and silicon are in tetrahedral sites. So now we have seen how this hexagon forms, hexagons of this SiO4 tetrahedra, they forms. Now the structure of zeolite that I showed you is zeolite A. Okay, these are commercial names. You can see zeolite A in the right hand side. Okay, right hand side top, and you can see it is made by as if some kind of this kind of football kind of some ball kind of structures. So there are 8 ball kind of structures, okay, and they're connected by a linker, okay, which looks like a box here, okay, and and this is extended in 3 dimensions. Now because of this, you can see that this is like a case structure. We'll come to what is a case, okay? But first, let us see this is exactly the zeolite is. Then you can see this is a case structure, and there are two cases in zeolite A. One is the beta case, which is or called the sodalite case. Okay, this is a smaller case, and there is a bigger case. Okay, this is called the alpha case or the super case. Okay, and the distance between this ball kind of structures is about 1.23 nanometer. Okay, so you can imagine the bigger case is going to be something like 1 nanometer. All right. So now the question is that if you want to get this kind of a structure, you have to get that ball kind of structure. And getting this ball kind of structure is not so difficult if you take, which means the beta cases. Okay, getting this beta cases is not so difficult. It is consisting of 8 hexagons. In the last slide, we said how hexagons form. Now, if you take such 8 hexagons, and if you connect to each other in a particular fashion, it forms this kind of beta cases. So once it forms the beta case, it looks like it has 8 hexagons and 6 squares. And so right, left and top, first model is the beta case, and the second one, you can see it has both silicon as well as aluminum. So this is the structure. So one important rule, okay, while making this kind of structures is that which is called Lowenstein's rule, which is Al4O4 tetrahedra are always interspersed between SiO4 tetrahedra, which means there are never going to be aluminum oxygen aluminum bond. Okay, each aluminum has to be separated from the other by at least one silicon atom, which is not necessarily true for silicon. So if you have aluminum and silicon, it can go maximum, up to 50% of aluminum, but it is usually less. So we discussed the inside cavity is called the alpha case, having 6 octagons, 8 hexagons, and 12 squares. If you see the alpha case, beta case is small, 8 hexagons and 6 squares. The alpha case is bigger, it has 6 octagons, 8 hexagons, and 12 squares. Now if you extend this, you see the right hand bottom structure. This is the crystal structure, where you can see there are two kinds of holes, cases, the yellow ones and the green ones. So this is one typical zeolite. So next, if you want to design more complex zeolites, how are you going to do it? So the way to do it is that I can see on the top left. Now we discuss only one alpha case. Okay. Now here there are more number of alpha cases connected to each other, and they are connected in different ways. So the first one and second one are connected in different ways. The first one is connected through hexagon. The second ones are connected through the squares. The third one is connected, two beta cases are connected with a linker. Now they become your structural units. Now if you combine them by different linkers, for example, on the right hand side, you see the linkers. Okay, these linkers are nothing. For example, if you see again left hand side, third one, left hand side top, third one, you see this looks like a square, as if a square is connecting two molecules, two alpha cases, beta cases. This is not the case. They are basically just two molecules. So similarly, you can have few molecules. If you have 4 molecules, you have linker which looks like D4R, or if you have 6 molecules, you have D6R. So 6 molecule is going to sit on top of the hexagonal face, and this D4R is going to sit on top of the square face. Okay. If they are directly connected, we get soda light, and this is what we discussed. Okay. No, it was not soda light. So you can see bottom left is soda light. Okay, and this is not considered a zeolite because this, even if you consider a cavity here, the cavity is too small, less than 0.2 nanometers. So it is not considered as a zeolite. So this is soda light, this is a mineral. Okay. The second one, Linde A. Okay, this is a molecular sieve. Okay, molecular sieve means something which can separate molecules. So here you can see the cavity is bigger because the soda, it is same structure as sodalite, but connected, this beta cases are connected with 4 molecules, and in the structure it looks like as if they are connected through a D4R, like a cube, as if they are connected by cube. If they are connected through hexagon, and the further side, you see that the case which is in between has actually increased now in size. So in this way, you can start with the basic motifs, tetrahedras of silicon and aluminum, and you can start building materials with different porosities. So we have been discussing about pores, but in reality, there are 2 important things when you really want to use them in some applications. The first is the cavity size or the pore size. But the second important thing is the window size. You might have a very big pore, but you have to have a window if you want to use that cavity for some absorption, for some catalysis. You have to have pathways through which the molecules from outside will go inside, and then again, once the application is done, it has to come out. For example, in catalysis, reactants go in and the products come out. So the reaction is going to happen in the cavity. So for example, you can have an activated complex forming inside the cavity, but it is also important the window size through which these molecules will go. So you have to tune both, and this tuning, the window size is different. So if you decouple window size and pore size, you can start having different applications. For example, you can have a small pore size, window size, then only small molecules will go. So reaction will happen only with the small molecules. Okay. So in case of sodalite, for example, the case is 6.66 Armstrong, okay, 0.6 nanometer, but window is 0.2 nanometer, okay. So the case is big enough to be called it as a porous material, okay, but the window is not big, it is just the borderline. So zeolite, the case is about 1 nanometer, 1.1 nanometer, window is about 0.4 nanometer. If you go to zeolite XY, where you have the linkers are hexagons, D6A, D6R. So in this case, the pore size is 1.3 nanometer, and window size is 0.7 nanometer. So let us try to see some zeolites in YouTube. different building blocks, and you can see the cavity. And you can see the third All right, so I have included that link. So whenever you want, I'll share these slides and then you can see. So if you consider all these things, so all the structures, the formula is the following. Okay, there are two ways you can write this formula. For example, AlO2x, SiO2y. Okay, these are tetrahedras. X and Y are their relative abundance, and whenever you put aluminum, so you have to put one more metal atom, which is M. X by N, if it is a divalent cation, so N is going to be 2. If it is monovalent, N is going to be 1. Okay, so that is X number of X by N number of metal atoms, counter ions. X is again Al2O3X, the same X, okay, for charge balance, where M is sodium, potassium, lithium, silver, NH4, H plus, calcium or barium. So N is the cation valency in this equation. So if there are two equations and two formulas, they are interchangeable. So the tetrahedra make up the three-dimensional framework with lots of voids and open spaces. It is these voids that define the many special properties of the zeolite, such as the absorption of molecules on the huge interfacial area. Okay. Now this is already you know, but what you do not know is that how much is the surface area. Okay, because of these voids, and these numbers are something like 500 to 1000 square meter. Meter square per gram. So 1000 meters square, you can imagine, it is something like your basketball court. If it is 100 meters square, even maybe more than that. So using 1 gram of material, normally if you take some, so for example, if you take sand, and if you get the surface area is something like 1 meter square per gram. Okay. So in comparison to that, this is very high surface area because of these pores, and that is why it is important for absorption of molecules and catalysis. So these cavities are usually occupied by water, but large enough to allow passage of gas species. Difference between various zeolites is manifested in content of hydrated cations, which occupies the pores and channels, the ratio of silicon aluminums in structure and number of water molecules. Zeolites are also known as molecular sieves, referring to the ability to selectively sort molecules based on size. So this is kind of a summary slide of whatever we have learned so far about zeolites. So influence of, so how the properties changes when you change the ratio of silicon to aluminum in zeolite. So zeolite with low aluminum are hydrophobic and vice versa, because obviously because of the charges. Okay. So Lowenstein rule we have discussed. AL linkage is forbidden. So silicon to aluminum ratio has to be bigger than 1 or equal to 1. If the counter ion is a proton, then this is hydrogen bonded to the lone pairs of the neighboring oxygen bridging atoms generated by generating Bronsted acidity. Okay, we'll see what is that bronze acidity in next slide. So it has acidic sites, and these acidic sites, the number of acidic sites depends on the aluminum content. Now, if you do high temperature treatment, can dehydroxylate the zeolite and generate Lewis acid sites, which means that the OH minus ions or water can go away from these structures, and then we can have Lewis acid structures, which means that only the electrons are lone pairs. Now, high concentration of protons gives rise to high acidity. If you have a lot of aluminum, you will have large amount of protons, and it is highly acidic. But if you have low concentrations, then you have stronger acid sites, okay, because its ability to release proton increases. So these are the acid sites. Okay. Normally, zeolites as synthesized. Now we can do an ion exchange with protons. If sodium is replaced by protons, then you have bronze-state acids. Now, if you take this bronze-state acid and then if you heat it, it will form, it will remove water molecule around 500 degrees. Okay, and at that time we will have, will get Lewis acid structures. So this is a slide where again there is nothing important here except that there are many different types of zeolites, and you will see that you can clearly see here the differences are in the amount of silicons and aluminums and the counter ions and water molecules. So in principle, the number of zeolites that you can generate in a laboratory is infinite because you can combine them in so many different ways. And this kind of work is mostly done in the industry nowadays because the basic understanding is nearly done. And so they keep developing new and new zeolites and making better catalysts. So finally, let us see a few examples of their applications. One important application is water softening. Okay. So you know what is hard water? Hard water is something which contains calcium and magnesium ions, and you know that they are hard water because if you use soap or detergent, it binds to soap and detergent. So soap and detergent becomes inactive. So, so if you take such hard water and flow through a column of sodium-containing zeolite, the sodium will be replaced by calcium or magnesium, and then the water will come out with the sodium ions. So, effectively, the water has become softened. So nowadays, many laundry and dishwashers contain zeolite. The ones that we use for almost everything, all the detergents use zeolite because it can absorb the calcium and magnesium ions. And you can do just, it is an ion exchange process. Okay, sodium is replaced by calcium, so you can regenerate it. Suppose if you have a water filter, okay, drinking water, it is also put in drinking water filters. So you can regenerate it. Okay, for regeneration, again you have to put sodium into it. So sodium is going to replace calcium or magnesium. So it is depends on the concentrations. The other uses are odor control and pet litter. Okay, pet litter means uh, those of you who has animals in their homes, cats and all. So when they do toilet or something, if it smells, so nowadays you have special arrangements where you can put this kind of mats, and it doesn't smell anymore. I had some. Okay, this is I think the last slide. I will see some videos. So ZSM5, again, the most widely used zeolite. This is used in safe selective catalysis, okay, reactant selectivity. So in the left-hand side top, you can see the structure of zeolite, okay, and so silicon is 93%. So this is, it has one-dimensional channels. This means it has channels which goes across the structure, okay, without changing its size. On the right-hand side, I have shown you how the channel looks like. Now you can see the schematically shown below is that you have these channels, okay, and these channels allow only certain reactants to go through because of size constraint. So others cannot go. So this is very, very important in petroleum industry. Most of the plastic related things, at least the precursors for anything which is plastic or organic waste, the source is petroleum. And petroleum, when you get petroleum, it has many, many things. It contains all kinds of hydrocarbons. So they have to be separated. So zeolites are widely used for separation. And this is the principle. The size selectivity is the principle. And this is a particular reaction, normal butanol, okay. And I think this is it butanol? Dehydration of alcohol over molecular sieve. While L-butanol dehydrates readily, secondary butyl alcohol shows great reluctance because it cannot get inside the pores. So product selectivity, okay. One is based on the window size. There is no window size there, for example. Now GSM5 is a class of zeolites. So this is another zeolite GSM5. So here we have these windows, and then we also have these cavities. Okay. Now paraxylene is far more valuable than ortho and metaxylene. Okay. It's very important because you make polymer using paraxylene. So if you get something like if you get paraxylene, if you mixture of paraxylene and metaxylene, you are doing this. So you start with toluene, okay, toluene and alcohol reaction, okay, methanol reaction. So it can give rise to paraxylene, orthoxylene, and metaxylene. But you see, so paraxylene and orthoxylene and metaxylene cannot come out because the window is small, so they will remain there, and then they will again undergo rearrangement. So ortho will become para, and meta will also become para, and then they will come out. So the product you get is exclusively paraxylene. So zeolites are also effective in removing radioactive particles from nuclear waste and cleaning up soil contaminants with toxic heavy metals. For example, in 2011 Japan earthquake, the big earthquake, when Fukushima, this nuclear plant was damaged, so this zeolite was used to scavenge the radioactive ions from water, from sea. So they have many applications, animal feed, even human feed, okay, medicines. because if you have medicines in them, these medicines get released at a control rate. Pet litter, waste purification, odor control, and catalysis, horticulture, aquaculture, because in aquaculture, because the water remains clean. Oil absorbance, you keep listening to such news that some oil tanker made with an accident, and then oil spillage happens, and then lot of noise because it affects the environment. So zeolite is used to absorb such oils. So I'll show you. Let us discuss the synthesis. Then we'll see a couple of videos and we'll stop this part. So synthesis is that as we know, it contains water. So the synthesis will have to take place in water. In fact, naturally also zeolite forms only where water is there. All zeolites are formed in aqueous solution. The water molecule acts as template, which are necessary in order to form porous structures. Okay, so water itself acts as a template. Instead of water, if you want to get bigger pore sizes, you can put some other molecules, which acts as a template. So one of the method is the sol gel method. Okay, and you get a gel, and the final treatment is under hydrothermal conditions. Once you get a gel, if you remember, we discussed sol gel method. So you get a sol first, then you get a gel, and then gel you do hydrothermal synthesis to get zeolite. Here is an example: sodium aluminum hydroxide and sodium silicate and NaOH. So at 25 degree, if you mix them, you get a gel. Okay, and this gel, if you take heat it about say 150 degree centigrade, you get zeolite. So the structure depends, and this process itself, you can start with the same starting materials. Now the final zeolite that you will get will depend on temperature, pressure, and you can also add some templates instead of water. The templates are usually alkyl ammonium cations. Okay, and these cations, alkyl ammonium cations, depending on the chain length, the pore size gets decided. So let's see. This is the final example of final slide in zeolites. So this is template synthesis. In this case, the cavity and the channel size is controlled by the building, control and maintained by building the framework around specific organoammonium cations. These cations can ultimately be converted to volatile products at about 500 degrees centigrade. So once you get the zeolite, if you heat it, the template will burn away. And but the case remains, retains the framework structure. For example, sodium silicate and aluminum hydroxide with tetramethyl ammonium salt. If you heat, you get sodalite. Similarly, if you take a bigger anion, then you get this ZSM5. All right, so let us see a few videos and then we'll close this session. This is, I think, about synthesis. This we have seen. Here.
Hi, my name is Ilke Arslan, and I'm a catalysis scientist at the Pacific Northwest National Laboratory's Institute for Integrated Catalysis. If this white powder looks ordinary to you, take a closer look.
So this bottle contains
This white powder
zeolite.
looks ordinary to you, take a closer look. Much closer.
This is an electron microscopy image, and just like NaCl crystal, which is like cubic, you can see here these structures are also cubic.
This is a zeolite. A zeolite is a crystalline material composed of
Can somebody tell me if you can hear the voice from the video?
Yes, sir.
Okay.
silicon, oxygen, and varying amounts of aluminum. This structure contains microscopic channels, sort of like a sponge.
You can see the channels.
There are hundreds of uses for zeolites. The kind in laundry detergent softens water so the soap can lather. In kitty litter, it absorbs liquids, and they're even used to create fuel for your car. At PNNL, our team is studying zeolites to understand how to make better catalysts. The size, shape, and makeup of the microscopic channels determine how the zeolite drives chemical reactions. However, scientists would like to understand more about the detailed processes that occur within these pores. We combine expertise in synthesis and characterization to unlock potential applications in zeolite catalysis. But before we can study these structures, we have to make them. And for that, we go to Mirek Derowinski, a catalysis scientist specializing in synthesis.
There are many ways to make the zeolites, but today I'm going to show you how to make zeolites of ZSN5 structure. First, we prepare amorphous gel containing silica and alumina mixed together with inorganic or organic template source. Next, the aqueous reaction mixture is heated in a sealed autoclave.
So you can see this is the hydrothermal bomb. We discussed what is the hydrothermal autoclave or bomb. So this is the hydrothermal bomb, and you can see inside is white, which is made of Teflon. Okay. Now this will be closed.
The aqueous reaction mixture is heated in a sealed autoclave source.
So they have made a sol first. They have not gone up to the gel stage. Now
the right combination of temperature, pressure, and time converts amorphous gel.
Now you can see inside this oven, the hydrothermal reaction is going on. You are shaking it at the same time. The reaction is
into crystalline zeolite. Now that we have synthesized zeolite, we can look at it with a scanning electron microscope. Here we can see its detailed structure and
different kind of morphology.
Begin to understand how changing the temperature, time of ingredients of its synthesis.
At different time, temperature, pressure, you get different morphologies.
The properties. For example, here you can see how changes of synthesis conditions affects crystal size and morphology of the same zeolite.
Using scanning transmission electron microscopy, we can get an even clearer picture of the structure. For example, in this image, you can see the crystal structure of the zeolite as
the channels here,
well as the brighter dots that correspond to small clusters of platinum atoms. The location, size, and distribution of the platinum atoms determines many important properties of the chemical reactions. Using electron tomography, we can reconstruct the three-dimensional structure of the zeolite on the nanoscale.
So I'd like to tell you that this kind of experiments we do in our laboratory. So we do not exactly make zeolite, but we make other catalysts, and we can have a look inside how this metal catalysts are using our TM studies. We'll discuss it towards the end.
Scale to obtain more accurate information.
So you can see how inside zeolite, how in this case zeolite is a catalyst support. Platinum is the catalyst. Okay. So this way, if you use platinum, you can recover platinum. If you use platinum as something like homogeneous catalyst, in that case, it is difficult to recover platinum.
Out of the hundreds of known synthetic zeolites, only about 15 are used for catalysis. Our work aims to understand what makes just biofuels.
Well, and then we have a couple of more.
Zeolites, amazing mineral structures found in nature. These microporous crystalline aluminosilicate molecular sieves consist of highly ordered discrete pores and cavities with
This is the crystal structure. You can see this structure is obtained from X-ray crystallography.
molecular dimensions making up a crystalline framework. This allows for small molecules to pass through while stopping larger molecules, useful for the absorption of gases and liquids. And for decades, these microscopic structures have been man-made, produced synthetically, and tailored to industrial process applications. Our range of products includes zeolite powders and extrudates for use within the industrial processes of petrochemicals, oil refining and chemicals, as well as within emission control applications, such as in catalytic converters and the decomposition of NOx and N2O. Clariant zeolite raw material production capabilities include well-known zeolite structures, which cover a wide range of silica to alumina ratios. On demand, most other common commercial structure types can be produced. A representative and characteristic zeolite beta application is hydrocarbon storage after the cold start of a car engine. At low temperatures, no catalytic decomposition of the hydrocarbons is possible. However, the zeolite beta, with its high capacity of capillary structures, provides intermediate storage for the hydrocarbons until the temperature of the exhaust gas flow is high enough to convert them to carbon dioxide and water in the presence of atmospheric oxygen. Mortonites are important in process catalysis. For example, they can be used to catalyze disproportionation reactions of carbon containing aromatic compounds. Methyl groups of two toluene molecules rearrange in the presence of the catalyst to give one benzene and one xylene molecule. As xylene exists in three forms, so-called isomers, ortho, meta, and para, these xylene mixtures can be transformed into one homogeneous isomeric form via another zeolite catalyst, such as MFI, in a subsequent step. Chabazites are able to adsorb water molecules from the gas phase up to 30% of their own weight. During adsorption, these water molecules bind to the zeolite surface and emit energy. This technology allows renewable resources, such as solar energy, to be used as efficient sources of heat, for example, in heat pumps to generate heat efficiently with low power consumption. The process is reversible and sustainable. The water molecules can be removed from the zeolite material so that the process can be repeated as often as required.
Okay, we have one last video. It's quite interesting. See, people who want to make careers in material science, there are so many different things one can do. It doesn't have to be a professor alone. In fact, these are things where you have very high returns if you work in these areas in industry.
Zeolite properties and its uses in livestock feed production. Zeofeed is a feed additive made of 100% natural cleanup tillolite, specifically intended to improve animal nutrition. It is used in the production of complete feed mixes, pre-mixes, and other specialty products. During the manufacturing process of feed, it acts as a technological anti-caking agent. It reduces the adhesion of individual particles in the feed and prevents the formation of lumps. After adding Zeofeed, the feed is easier to mix and mold and is dry and loose. It also binds free water, ammonia, and reduces the risk of contamination of the feed by molds. Zeofeed positively regulates and stabilizes pH and prolongs the absorption of nutrients through the digestive tract. Its specific affinity selectively captures ammonia, water molecules, toxins, heavy metals, and digestion metabolites. Zeofeed thereby decreases the energy needed for metabolism, and this available energy can be used to improve growth rates, immune health, and animal productivity. It is chemically inert, does not metabolize in the digestive tract, and reduces scours in livestock. Zeofeed has a three-dimensional structure, forming a network of cavities and channels that are 0.4 nanometers in size. This means that it does not absorb larger nutrient molecules, such as vitamins and amino acids. Zeofeed stimulates secretions in the digestive tract, promotes intestinal peristalsis, and helps improve the utilization of the passage of antibodies through the wall of the small intestine. This increases the efficient usage of available energy in the feed, which results in higher production and a higher quality meat, milk, and eggs. The use of Zeofeed in feed mixtures has a significant and positive environmental impact as well. The wastes generated by animals consuming this feed mixture have much lower ammonia content that is released into the environment, and nitrogen recycling occurs. Wastes are not environmentally toxic, resulting in a safe organic fertilizer with nitrogen content. The result is an improved environment for people and animals.
All right. So, this brings to an end to discussion on zeolite. Do you have any questions? So in the next class, we'll try to see some more porous materials, such as MOF, metal organic frameworks, and if possible, maybe polymer organic frameworks. So do you remember how many classes were left with? When is your last exam? Last class? I think, is it on 15th? Does anybody remember? So I think until 15th we have time. So we roughly have 1 month left. So we'll discuss some aspects of nanomaterials, characterization techniques. Maybe that will take us 2 to 3 classes, and porous materials and organic materials, maybe another 2 class, and then we'll have superconductivity and magnetism. So I think in about 8 to 9 class we're going to cover. Is there anything special that you would like me to cover? Because I have not been able to do justice to all the topics, because we are basically touch and go. We are not going deep into the subjects. But if there's anything that that you'd like me to teach from the literature, from the syllabus, please let me know. Okay, let us take a 5-minute break, and then we'll see some aspects of or I have a meeting at 4. We have a departmental meeting. So I think around 3:50, 3:45 I have to stop. Okay, I give a 5-minute break, and then we'll see a little bit of defects.